Let's take a few minutes now to look at confidence intervals. And this will be an introduction, so I'm not going to get into any number crunching here, but rather I'm going to try to lay the conceptual foundation for what we'll be doing over the next few weeks. Let's first look at quantitative data, where we're measuring something that can be quantifiable. For example, let's consider all the fish in Lake Michigan, and we're trying to get the average fish length. So our population might look something like this. We might have a lot of small fish, maybe even more medium fish, maybe some large fish, and maybe there are a few very, very big fish, perhaps at the bottom of the lake. And the average fish length will be our population parameter, and it will be mu. And our fish will also have a standard deviation, which we'll call sigma. And those two together are called parameters, and they are population parameters, and they are two values that we will never know because we can't conduct a census and measure every fish in the lake. However, what we do like to do is take samples. So we're going to sample from this population, and our sample might include, say, 50 fish or 100 fish or 1,000 fish, depending on how elaborately we want to conduct our sample. But we're going to get a variety of fish. I'll call them X1, X2, X3, all the way up to some final fish Xn. And that sample will have a mean, and it will be a sample mean, so I'll call it X bar, and it will have a sample standard deviation, which I'll call SD. And those are sample statistics, and they will vary from sample to sample. But what we hope is that if we sample well, in other words, if we stratify, for example, and we get some fish from the top of the lake and some fish from the bottom of the lake and some fish from the middle of the lake, we also get some fish near land, some fish near the middle of the lake, so that we're making sure we get a representative sample. We're hoping that this X bar will be fairly close to the population parameter mu. And we also hope that the standard deviation of our sample will be somewhat close to the standard deviation of the population. But we know in the end that our X bar will not probably exactly match mu, but we hope we're going to do a good job. What we do next is we create what's called the sampling distribution. And the sampling distribution is hypothetical. What we do is imagine that many people are replicating our sampling technique, and they are all getting different X bars, just like we got an X bar. And if many, many people were to do just what we did, we'd get the sampling distribution. And our X bar might be over here, but somebody else might get a different X bar over here, and somebody else might get a different one over here. And if we started to collect all of these, they'd start to form a distribution. And if we collected enough of them, they would start to look normal. It would create what's known as the normal distribution. And what's amazing is at the center of this normal distribution, in other words, the mean of all our X bars, will be the mean of the original population. And the standard deviation of all our X bars will be the standard deviation of the population divided by the square root of our sample size. And this is a pretty powerful idea because it allows us to see where our individual sample might sit in a collection of many, many samples. So here is our little X bar right here. And what we hope to do, because we know that our sample isn't necessarily a perfect match for the population, is we create an interval. So we spread our arms and we create what's called a confidence interval. And we hope that that confidence interval will capture the true mean. Now, for this theory to work, in other words, for our samples to distribute themselves normally, like we see here, several conditions have to be met. And we're going to talk about these conditions in more detail and with more specifics a little bit later. But for now, I just want to convey that there are three general ideas. The conditions for this sampling distribution to appear normal. One is that our sample has to be collected randomly. If we do not do a random sample, in other words, if we get all our fish from the bottom of the ocean, for example, or all the fish from near the shore, then we will not be centering our means near the population mean. We will be consistently too high or too low. The second condition that must be met is that our sample must be sufficiently small. And the reason why that's important is that we want our sample elements to be independent of one another. We want x1 to be independent of x2 to be independent of x3. We want all these fish to have no relation to one another necessarily. And once we sample a huge portion of a population, they no longer are independent. And the third condition is we want our sample to be sufficiently large. In other words, if we sample only 2 fish or only 3 fish, then this sampling distribution won't appear normal. We need a sufficiently large sample. And for quantitative data, typically if we get more than 30 elements in our sample, we can feel confident that the sampling distribution will indeed have this normal shape. Let's now look at categorical data, and a lot of similarities will occur. With categorical data, we're looking at a proportion of people who, for example, have some trait, like red hair, for example. And we know that out there in the population, there are a certain number of people with red hair, and they represent a proportion, which we'll call P. So here's the proportion of people with red hair. And then there's a proportion of people that don't have red hair, and we'll call them Q. And just like before, P and Q are population parameters. They are things about the population, measurements in the population, that we will never actually be able to quantify precisely. Now, what we do instead is we grab a sample from that population. So we're going to go ahead and grab a bunch of people from our population, and if we sample well, we hope we're going to get a representative sample, and we're going to get our own sample proportion of people with red hair and our own sample of proportion of people who don't have red hair. So we're going to get a P hat and Q hat. And these two things are sample statistics as opposed to these two measurements, which are population parameters. So this is our sample, and it has a certain sample size, n, the number of people that we sampled. Now, just like before, we are going to take this information and then imagine a sampling distribution. So we're going to now take our P hat and imagine that many, many people are replicating our sample and getting their own P hats. So our P hat might be here, but many people are going to also get P hats when they conduct their own samples. And these P hats will start to distribute themselves normally, just like before. And this normal distribution will be centered at, in other words, the mean of all our sample proportions will be centered at the true P, the population's true proportion of people with red hair. And the standard deviation for all our P hats will be the square root of PQ over N. And what we will be doing is taking our individual P hat, this one right here, for example, and we will be spreading our arms and creating an interval. And we hope that this interval will capture the true P. And just like before, there are some caveats, some conditions that have to be met for the sampling distribution to become normal. And just like before, we need our sample to be random. So we can't purposefully go into areas where we know we have lots of red-haired people and get a P hat, because then we will bias our results. Also, our sample has to be sufficiently small, so we have to make sure that we are sampling typically less than 10% of the population. And then finally, we want our sample to be sufficiently large. We want to sample enough people so that we get a representative sample. And that typically requires that we need at least 10 successes, in other words, 10 red-headed people, and at least 10 failures. So in this case, that would be at least 10 people without red hair. And that's it.